Going live. I think we're live. What's up? If you can hear me and see me, put it in the chat. Happy Sunday, everybody. I'm here in my garage. Just bought this new Lamborghini here. Awesome 5x5. Thanks for joining, folks. We are here to mill a couple of parts for the meat rocket. And actually, the first thing this will fly on is send it. But why don't I tell you a little bit more about what we're doing? Pretty chill stream today in terms of quality. So hopefully you don't mind that. You know what we could do? Here we go. I'm going to start overcomplicating. It's my favorite thing to do. We're going to overcomplicate the stream. This is going to be transform fit to screen. All right, that's fine. It's good enough. Okay, so here's the plan. I'm here in my garage. I got my forklift certified shirt on, and I need to mill a couple of parts for the meat rocket. So basically, on meat rocket, and ideally on send it before then, but I have this goal. In my pursuit of a space shot, I want to get some of the best footage and like video from this flight that people have seen, like from a space shot level rocket. You know what? Let me overcomplicate this more. Let me put you guys on a box so that I'm not like talking down to you. Let's see if this helps. What is the likelihood that this is going to disconnect my entire setup? High, I think. High likelihood. Okay, that's a little bit better, I guess. So I want to get like this really stable video, right? And one of the ways, so like there's a couple of ways to do that. The big problem is that the rocket spins as it goes up. So it's like spinning a ton. You can, someone actually tweeted to me about this today, but you can like get your fins pretty straight on the rocket. But once you're going like, meat rocket goes Mach 3, space shot goes like Mach 4.5, Mach 5. And at that point, like, it's going to be really hard to fight even the tolerances that this wonderful machine can do. So, like, the rocket's probably going to be spinning. And especially for the space shot, spin stabilization is how we keep that upper stage more stable than it otherwise would be. So, like, all of this creates this problem where the footage is like, and you've got all this motion blur, and, like, if you have any idea about, like, how global shutter versus, like, scanning shutter works, you get like jelly video basically. So like it records line by line, and because you're spinning so fast, the whole image looks like this. That's a problem. You could use a 360 camera. I don't know if 360 cams do global shutter. I don't know how that works. The 360 problem is that you have to get the lens over the edge of the airframe. And for both lenses, or all four or all three, however you have your camera set up, it's a little bit tricky to get those dimensions right, so you need like a 360 camera that has remote lenses and remote sensors. And I'm not looking to do too much experimental stuff like within the camera world. All of this is to say, the idea that I had, and I saw someone else do it pretty successfully, is we could de-spin the camera, so the whole rocket can still spin, and then the very small section of the rocket, it's not a big mass penalty, it's not a big reaction wheel, the very tiny part of the rocket that houses the cameras, that gets unspun. That like de-spins itself. So, I don't know if it'll work. I found it really hard to like gear the motor. You'll hear more about this in like an upcoming VPS video, but part of this, whether you want to spin the camera or not, if you're going to go Mach 3, you need a shield for the camera. If you're going to go Mach 1, you probably want a shield. But like, you need a shield to protect these little run cams that I have. And so what I've got here, I actually should have set up a CAD view. But I'm going to set up the machine a little bit, and we're just making two tiny shields, like little aero covers, little fairings for the for these cameras. And it's just out of aluminum. I have some bar stock here. So I cut these two pieces. These are 1 inch by 1 inch blocks. And so it's just 6061. It's nothing too fancy. You could do this out of fiberglass probably and get away with it, at least for Meat Rocket. The nose cone for Meat Rocket has high temp epoxy in it, but everything else is fine with just regular fiberglass. All right, by the way, shouts out everyone for joining. I can read off some names here. Oh, wow, we have Elon Musk. Thank you, Elon. Thank you so much for joining, buddy. Good to see you. All right. Rancid Marshmallow. We got Reva. It's Jolie, the Flying Eagle. Josmel, the Builders. Jake. We got Hamza in the chat. We got, I'm going to start skipping names here. Charlie. We got Linecraftman. We've got Tiff. Shouts out Tiff, who up de-spinning. We got Hannah. Hannah asks, hello, I have $7. Can I build Scout? Yeah, go for it. Got Forge Gamer. We got all these MFs in the chat today. Apologies for calling you all MFs. All right. So we have 2 ops to make this camera housing. I should get you like some type of screenshot with it. The problem is the cat is going to get mad if I like move from machine to machine. You'll see it as it shows up. How about that? It'll be like an exciting stream. So we have 2 ops. There's a top operation and a bottom operation. For something like this, you could do it with a 4th axis. I got the Tormach Micro Arc, which is the 4th axis on the machine. I haven't used it yet. I'm pretty scared to do it, but we are going to need that for the fin can, which I will absolutely stream as well. That's going to be like a 12 to 14 hour operation. So we'll be here for a hot minute. But we're starting off simple. I'm going to get this in the vice jaws. We'll make sure we are all squared away too. We should probably do that first in the vice. So we're going to be dial indicating. We're going to be putting in some parallels. It's great. It's going to be a really exciting day. All right. I got my parallels here. Why don't we get this vice set up first? And I can give you the little GoPro view of that. I've got a GoPro set up here. And my goal is to have this as like a semi-permanent view. Or something close to that, maybe, question mark. But something that I can like leave in the machine for a while. Ouch. Woof. Watch out. So, trying to get this roughly in the middle of the table. And then we're going to anchor it down with these 2 things. I always get a little sketched up by only using 2 of these here, but it has not failed me yet. 1 second. Try to get the mic a little bit closer so you can hear me better. Okay, hold on. All right. Is that good? Can y'all hear me? Okay. So first we get the vise in here and make sure the vise is far enough forward that we have good travel in both directions. We can also bring this down. So you check your travel. All good. So we can anchor it here. I'm also going to take this out and put in no tool. It's not good to leave this collet empty. Can bend it over time, but if I leave in no tool here, I can't like cut my hand as I'm moving back and forth, which is a thing that I used to do a whole lot before I started doing this. So where is my dial indicator? Okay. This thing is awesome. Probably going to be some boring parts of this stream. Machining is really cool once the op is running, but I feel like so much of it is just your setup and work holding. as like 90% of the work that you're really doing. Okay. So dial indicator is here, and what we're mostly looking for is along this edge right here. What's kind of our, it's not, I guess it's technically run out. Okay, I've also kind of got this at a tough angle, but we're going to clear the jaws on that. And I'm also going to tighten this vise down a little bit to start. And then we're going to start to like hit it back and forth with a hammer to actually adjust it. Okay. So let's get our speed nice and slow, and we're going to go back and forth on the y-axis here. And we're going to creep up on it using the x-axis. Nice and slow. Can y'all see that there? Oh yeah, you can totally see it. So we can zero out our indicator, which we don't really need to do. You can do it with this arm too. And it doesn't really need to be 0. These parts are not that precise. It just needs to be close enough. So when we travel along the y-axis, you can already see that dial indicator moving, right? That means we have, that means we're not centered. So what I'm going to do is I'm going to bring it to the rotation point, which is back here. These are also tenths too. They're really, it's quite sensitive. Am I going the right direction? Okay, I think I tightened it a little bit too much, so we'll... Yeah, there it is. So see, our runout's a lot less. Our dial indicator is not moving nearly as much. If we come all the way out here and hammer it down again, much better. And for our purposes, these are tenths right here. This is going to be plenty for us. So now we can take this, we can get rid of our dial indicator because it's super delicate and we don't want to hurt it. Put it over here. And now we can really tighten down the vise. If I were a good machinist, what I would do too is I would tighten down the vise and then I would check it again with the dial indicator, because tightening it down I think can theoretically change your alignment a little bit. But I'm Joey B, and we're not going to do it that way today. I'm also not paying a whole lot of attention to the chat. Shouts out to the chat, who I am not paying attention to. Cobalt as well. Am I the only one getting some skipping? Hopefully not. How does this look? That looks okay. It doesn't show any dropped frames on my end. No skipping. No skipping. Yeah, maybe just refresh. Yeah, I'm all plugged into Ethernet too, so we shouldn't have any like Wi-Fi problems or anything like that. Okay, so the next step is to hold our work in here, and what we're going to do is use something called parallels. Parallels are really cool. These are super precision. I think they're ground. They're precision ground parts that sort of do what you might think by the name. They go in your vise, like that. You know, we need to mill this 1-inch stock, but that falls all the way down. So how do we put it in here without having it be slanted? We use something called parallels. Put them in here, like this, and because these are super precision ground, you know that your stock is going to sit flat on top of them as it would otherwise, like on the base of the vise. These are not tall enough for what we want, so it might take some guessing and checking. We're going to hold on to it real, it's going to be a little bit sketchy. Yeah, see, that's still too much. The grip that we're going to have on this is pretty light. I think these have, yeah, don't look too close at these ones. These ones have a little bit of, I took a chunk out of those. Yeah, so this is pretty much our grip on the part at the top. So we tighten it down just a little bit, and then we take the dead blow hammer and we make sure that it's a little bit tighter. It's all the way down on the base. What we can also do here, if we want, so I could take that dial indicator again. Okay. Take this, put it on here. Okay, this is a little janky. Like this. And you can't see it that well, but I can, and I can check to see how much vertical run out we have. So we'll do that on the x-axis. Yeah, there's like none there. Cool. So our parallels are working. This is what we want. Take this off. Okay, percussive adjustments. So our clamp is tight. Our clamp is tight on the like the work table, and our clamp is tight on the work piece of stock material. Now we have to zero in. So we're using two tools for these ops. I'm going to go ahead and load the op here. Oh man, next time I do this stream, I should live stream the Tormach like computer view. That would be cool. All right, files, meat rocket, camera spinner, C hood top one. G code. Oh, right, and then I need to use, hold on. So one thing I wanted to do with this is use the active probe. I have a probe for the machine, and the probe knows all about all of its own parameters. What makes that cool is that I don't have to do that little paper slidey thing to zero in my machine. I can just touch the part with this probe. And the only thing that I shouldn't do is start the spindle. That would be bad. Excuse me. Okay, this is tool 99. And then we can go into probe ETS. And now I can do find Z. So that's our Z0. Is that true? Oh, are we in metric? Where are we in G21? Yeah, G20. Is it because we haven't run this? Okay, hold on. Okay, there we go. Now we're back in inches. So we're going to go back to offsets, probe. Okay, and find Z minus. Oh, here we go. Okay, we've set our work origin. This, am I close? Okay, 0.9976. So this is pretty close. If we go to 0.5, shoot, how do I do this? So what is, oh, my brain is broken. Hold on. 9976. I mean, I might just guess on the Y. Is that a bad idea? Certainly looks right. Hold on 1 second. Tip diameter. This should be, I want to make sure the probe tip diameter is right. Oh boy. Okay. What is the tip diameter of this device? I just want to double check. Because our probe is showing a slightly smaller part than my calipers are. Where are my calipers? Why don't we just do it that way? Yep, 1157 and 1157. Awesome. So this is exact. So let's try this again. If we probe, so I go down here, and I find the Y plus, and I set the work origin. Okay, so this side is now 0, and then whatever this measures, we divide in half, and that is our new size, like 90% sure. So we find Y minus, and it's 0.9972. So what is 0.9972 divided by 2? 0.9972 over 2 is 0.4986. So I'm going to go there on the y-axis. What was it? 0.4986. Cool. 0. All right, our y is zeroed in, and then we have to do the x-axis. So we'll go here. We're going to find x plus and set the work origin. Okay. And if we do it again, it should show us the change, which should be almost nothing. Yeah, 4/1000, or 4/10. So then we go down here, we take whatever this is and divide it by 2. 2.9908. This one's less important, but 2.9908 2 is 1.4954. So we go up here. Okay, cool. We have referenced all of our axes. Got the right tool in there, and the first tool that we're going to use is a 1/4 inch bit, 1/4 inch end mill. Not a bit. In fact, we do not call them bits. Is this 1/4 inch? This is 1/4 inch, right? Yes, that is 1/4 inch. It's like bigger than 1/4 inch. Am I reading that right? There it is. Okay. All going well so far. It's a slow process. Chris is the goat. Oh! Yo! Chris! My brother in Christ! Or whatever religious affiliation you have. Thank you for the super chat. It's very kind. Chris, can I do anything for you? Can I set the machine to a certain color? Let me know what color you'd like the LEDs in the machine to be, and I'll make it happen just for you, dude. Thank you for the super chat. Okay. What's up, folks? Do I still use my Nomad 3? I do. I actually, well, sort of. I tried to use it last week to cut this little carbon fiber plate that holds a motor, and one of the axes on the machine, the stepper motor, is really upset. The stepper motor is not happy, so I've been using only the Tormach right now. This is not clean plexiglass. Let's just double check. Let's do like a little bit of sanity checks here. So we're using tool 2. And if I go down here, this should be, I haven't checked tool lengths in a while. It should be like a couple thou off the bed. And it's not. See, this is why we check things. 1/4 inch. Tool 2. You know, this is not worth it. Should we double check the tool length? It's 3 inches off, which tells me I think something's wrong in my probe setup. Let's not worry about it. let's re-zero here. Okay, here we go. So this is Z0. We've got our G code loaded right on top. I'm feeling pretty good. Are we all feeling pretty good? Should we start the cutting? Actually, before we start the cutting, why don't I clean up this window and give you guys a better view of what's happening. One moment. Boy, this is not coming out that clean. Here we go. That's better. There's a lot of dust on these windows because I haven't been done any like hardcore machining in a minute. But boy, oh boy, is that about to change. All right, that's pretty clear. Let's get a camera in front of it. Too many wires. Okay. So, let's see if this works. Where's that reflection coming from? There, that's better. Is everybody feeling lucky? The forbidden milling milk. Oh my god, good call. We have to turn on the milling milk. Thank you, Hannah. The milling milk got turned off recently. Yeah, there it is. That's disgusting. Oh, man, I love that smell. That smells like early Scout development, and it smells like Send It. That's really nice. Milling milk. All right, let's do it. Let's send it. So I have tool 2 in the spindle. 1/4 inch end mill. We're going to start it at half the feed rate and see how it does, because I always mess these things up from time to time. So let's not push our luck too hard. I'm also going to make sure all right, we're going to record on this, just in case. Can probably go faster. It's also a pretty shallow cut. A lot of the settings that I created for this bit, or this end mill, this 1/4" end mill, a lot of those settings were derived from a much longer tool stick out. So because our stick out is, you know, maybe on the order of 1 inch here, I could probably take more aggressive cuts. Basically, with a lot of, it wasn't Sendit's parts, especially the reaction wheel for Scout F, I had to have a really long tool stick out in order to get like the radiuses and depth that I needed in some of the parts, which makes your tool really wiggly and a lot less rigid. So I broke a couple of bits, and then I got really conservative with my typical settings for these end mills. This is also too much coolant. We do not need that much coolant. And it fogs up the whole garage eventually. Can you hear me okay when I talk, by the way? We can probably speed it up. And the nice thing about these parts right now is that all of these are adaptive tool paths, so they all have pretty constant tool engagement, or like ideally, and it's only 2 adaptive ops. So there's a 1/4" adaptive op, and then there's an 1/8" bit that we use for a really tiny finishing step down. And that's pretty much the situation. Who needs fish and chips when you can have milk and chips? You need at least 5 more mics. At least! Okay, breakfast queen boss. You can get the GoPro view if you want. The color temperature is way different on the GoPro. The Z-Cam, like, auto color temperature is not a great guess. Has anyone seen what Chris Kidd said? Did he give a color? So Chris Kidd donated $50 of Super Chat, and I asked what type of color he would like for the CNC. And I don't see it. Chris was silent on the color. Chris, you have 1 minute. Oh, here we go. Builder's choice. Okay. Well, I know what I'm choosing. Got that rainbow. Oh, this is all messy again. I gotta be completely honest with y'all. I gotta be open and honest right now. This is the smoothest start to milling anything that maybe I've ever made. We measured everything, I double checked my work, I pressed go, and it kind of started just working, which is not how it usually goes. Is this stuttering for anyone else? Is it just me? Looks like it's stuttering. Does it stutter on the GoPro? Yeah. I wonder what that stuttering is. Does it get worse with more light? Is it encoder problems? It could be. I think it's probably the encoder, because it's not the camera. some music up in here. Oh, I wonder if it's the frame rate. It could be... No, it doesn't seem to help a whole lot. 1080. That also didn't help. Alright, let's switch to the GoPro for a hot minute. Dcam is coming back. Maybe it's the cam link? I would be surprised if it must be the encoder. We could turn our bitrate down. Alright, we're back up to 100% feed rate here. We're starting to hit the chip clearing stuff. It's still jumping around. Alright, I have another idea. I'm going to get a fan to put under my computer, and we're going to try to cool my computer down, because Apple makes ovens that duplicate or are dual use as computers, but they mostly make ovens. So we're going to try to cool that oven down. I put a fan under my computer. We're going to see if that fixes up some encoder issues. Nino asks, Joe, will Phineas ever fly again? Maybe. I don't know. It's sort of just like sitting around. It might fly again at some point, but I don't really have any plans for it, and I've changed the way that I think about how I want to do aerodynamic control so much that it doesn't seem like it would really be worth it to fly it again. Now we have to see if I'm going to crash into my vise here. I don't think I am. Yeah, we have one more layer to go down. We should be pretty safe. Charlie thinks I should put the mist cooler on the laptop, which is an interesting strategy. Is this the camera cover for the meat rocket? If so, also what is the meat rocket? So the meat rocket, this is the camera cover for the meat rocket. It's one of two. There are at least, ideally, I think there are going to be 3 cameras on the meat rocket. There's one looking at the horizon, and there's 2 pointed down at the fins. The 2 that are pointed down at the fins, one is going to do straight 4K, 30 frames per second or whatever, so you have nice high resolution stuff, and if the camera D-spin works, that's going to be beautiful footage from the rocket. The other one is going to do 1080p at 120 frames per second. So if we do spin, I can still recover some usable video. And that also, like that redundancy also gives us a little bit of peace of mind in terms of how often I usually lose cameras. So that's sort of the strategy there. Someone says SpaceX just posted an image of the Falcon Heavy. Woof! Yes, they did. That is pretty hot. All right. We should be nearing the end of this op here. I think I still have too much coolant. Alright. How's everyone doing? Meat rocket is a rocket covered in slices of meat that cook when it hits Mach 3. That's a pretty good description. Oh, okay. You done, buddy? Do you want another tool? I think he wants another tool. That's what I think. I think he wants this. All right. That is an 1/8 inch flat end mill. Gonna hit cycle start. It's gonna ask us to put that in. That's tool 3. And we can double check at the top of the G code. Tool 3 basically says 1/8 inch. So we can, oh, I need to reset this bad boy. He's gonna gonna have to move a little bit anyway. This is gonna take a hot minute. So this is basically one long finishing pass. Okay. Good job with all the progress on BPS. What software do you use to create your PCBs? So I use, what is it called? EagleCAD by Autodesk. It is okay. It's fine. You should probably, if you're starting, you should use KiCad or KiCad. It is free. You don't have to pay $1 billion a year to Autodesk. I am sort of in the process of like switching away from Autodesk stuff because they've made a couple of decisions in the last few years that make me think like I don't love the way their business model is going. I would recommend KiCad, but I don't use it right now. When will your Starship fly? Honestly, I don't know. I think maybe after we do Meat Rocket, we go back, do a little Starship stuff, and then scale up a bit. Joe, are you SpaceX rocket? What? Can you clarify the question? You should be able to see what we're doing here. We're coming in, we're taking really tiny bites out of the material because we want to create what's, you know, kind of like a 45-degree angle, but it's not easy to do that without a 5-axis mill, and you can do this nice facing stuff. And the next best thing is we can create a lot of really tiny step downs that result in a pretty fine, like, tooth thing. And then if we really wanted to reduce every bit of drag that we could, which we kind of do, we could take this and we could hit it really quick with a little sandpaper and smooth out all of the bumps that we end up with. But I think you'll see we should get a pretty good finish by the end of this. What is your opinion on KSP2? It's hard to have one. It looks really exciting, and beyond that, I hope it, you know, lives up to the hype. I have faith that they are doing the best job that they can because they delayed it quite a bit. So I have faith that they are doing the best that they can. Are you going to finish this with a ball mill 3D profile, like a I think in Fusion they call it like a parallel thing. My plan did not involve finishing with one of those. It felt like with the fine step over that I was doing, it would be easier to just clean it up with one of these. We'll see how that comes out. It's quite, like, you can start to see at the top of this step down, it is really fine. Kind of mesmerizing. I'm gonna be honest, I'm a little concerned about our tool length. You guys can watch this. I'm gonna go check something in Fusion. We have all our tool stickouts noted in Fusion, but I'm a little concerned that I may not have enough tool length to like really do this. Oh boy, hold on. The ice cream man is outside. You're not going to be able to hear him with this machine. Yeah, you can't hear him with the machine running, but the ice cream man is driving by. Alright. Yes, I went to check the tool length versus the object. It should be fine. Fusion thinks it will be fine. Yeah, Fusion thinks it will be fine. We'll see. We're gonna let it run. Will you ever go back to your Falcon Heavy? It's so iconic. Thank you. I probably won't. Not at least like how it was built before. I might do another one, but it would be totally different. Or like the way I build it would be different. And I saw one other question. I don't know what it was. When will you be releasing your music? At this point, you should just assume it won't happen. I really want to, but every day I wake up and every week I've got like some project going on that feels like the most urgent thing in the world in order to meet the other timelines that I have. And that results in really cool but not super urgent things like releasing music just always getting kicked down the road. I can use a bit with a 45-degree cone tip to get a smooth angled side. I totally could. Yeah, it would work. And yet here I am not doing it. Hydrodynamically steps on the planing surface can help break surface tension and increase the speed. Right surface with an increasing speed. I think I know what you mean, Brent, and I am not the person to answer it. I do not have the aero knowledge to answer your question. Stepped finish is less draggy compared to smooth finish because the steps trip the boundary layer and keep the turbulent flow attached. Is that really true? How tall are you in plank lengths? Well, I can tell you, it depends who you ask. On a good day, I'm like 5'11", and if you squint really hard, you can just round up to 6 foot. But I'm mostly 5'11", whatever that is in plank lengths. Why don't you finish the face with a vertical tool path to the steps? Oh, that would work too. And yet again, here I am not doing it. These steps are small enough though that like I can just sand it off too. I could do it in an operation, or I could just sand it. How tall are you in scrambled eggs? It depends how much you scramble them. Would you ever think of going into liquid-fueled rockets? Yeah, I think I have enough stuff going on right now that it's like not that important or feasible. The biggest thing that I'm doing right now is really slow development on space shot stuff, and that is going to cost an amount of money that will sort of require that I don't do a liquid project for a little bit. Launching another Christmas tree this year? I hope so. I got a new motor for it. We want to fly it. It was an M. It's not the M1560, but it's an M motor this year. So we had an L1000 last year, and then I found an M with comparable thrust, but basically 3 times the burn time. So we want to build a very similar tree this year, like a very similar base and everything like that. And we can use the existing stuff, like it'll work with a 4-inch tube, but we make the Christmas tree a minimum diameter rocket. And then we just see where it falls apart. Like I expect that this year, if we do that Christmas tree, it will fall apart on the way up. And we'll get to find out when that is. Is the tarmac, the Tormach really this quiet, or is there some sound suppressing in the stream audio? Let's do this. I'm going to stand equidistant between the microphone and the machine, but it's easy to talk to people over the sound of the machine. So like, I'm about equidistant between the microphone and the machine right now. It's not quiet. Like, it's not a very quiet machine. Or rather, oh boy, hold on. Woo! Is that the bottom? You know, I don't think the machine is going to crash. I don't think it's going to crash, but it's not because I'm good at my job, it's because I'm lucky. Oh, you loved the the Grim00 says, I loved the 6-hour cut as well. I hope you loved it. It was kind of like, I don't know why I did it that way. I had 17 hours of footage and I cut it down to 6, and it made me like high-key depressed for a week, but it was totally, like, just spending that much time in front of Adobe Premiere, I think it was worth it. Like, I think it's worth having all of that stuff in a place where someone can get to it. Like, I don't know how to describe it. I really like documentation in that form, and every now and then, like, I'll open that 6-hour video and go to some random point, and it's like, boom, this memory that I forgot about is there, and I can remember it. So if I can describe what's going on here, this inner part, this part that I'm milling down right now, the face that we're milling is going to be epoxied onto the inside of the airframe. And the face that sticks up at a 45-degree angle, that part pokes out of the airframe and then shields the camera. If you have an idea of like what these run cams look like, you'll sort of know what we're going for. But as we keep milling things down, you'll see it more and more. Oh, and that's it. How about it? Good timing with the air compressor, too. Okay. Excuse me. All right. So, this part is not done, but that operation is done, is what happened. Okay, let's get this out of the way. So if I wanted to do another operation here, I could, but like, I don't know. This feels smooth enough to me. It doesn't need to be that good. But we do need to probably deburr this a little bit. We were taking small enough cuts that I think we were like rubbing on a lot of the material. So there's just a lot of tiny little burrs on here. Oh, that's not that bad. I don't know. Once you take the burrs off of the stepped part, so like you could see these like intervals with the steps, right? Also, what is going on? Oh, I highlighted the thing, that's why. You can see these like intervals with the stepped parts right here. And those totally go away. That's a function of like these little burrs on the part. So the steps are actually pretty clean. I can show you if we take it out of here. But yeah, there's nothing left to do on this part. But it's always nice to like, don't immediately, I have to like tell myself, do not immediately rip the part out of the vise, just in case. Because you've already got your work coordinate system set up. If I wanted to do any other ops here, I could. I just think that there are a lot of parts to make for this vehicle, and it's probably not worth doing another op. What do you think? I could do vertical parallels with a ball end mill across this like 45-degree section. Put it in the chat. What do you think we should do? If we don't do that, then I take it out of the vise, I flip it over, and we mill out the inside. So let me know, shout me out in the comments down below, what should we do? Should we leave it in there and then ball end mill the top and get try to get a smoother, straighter finish on here? You can do that. It'll just take a second. I also don't have a ball end mill set up right now, but that's a pretty fixable problem. Don't I have another collet like this? Where is that? Yeah. Here we go. Just put a new tool in here. ER20. And this is an ER20 collet. All right, let's see what the chat thinks. Ball, 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 inside, ball. All right, screw it. Let's do the ball end mill. Some people wanted the other version, but don't worry. Doing the ball end mill just means you get 1,000% more Joey B content. It is going to take a second to set the tool up, though, because I don't have... I'm putting it in a new collet, so... did not have a ball end mill ready to go. Okay, snap in. Actually, you know what we can do? So I can just show you this process, but from across the room. Here you go. So basically, got all these end mills, and then you have to hold them. So we use something called a collet, which like clamps down onto the tool. And in order for the machine to do a good job of what we need it to do, we have to give it a really good sense. Carbide. Is this it? I think this is not. This is just flat, right? That is flat. I think I trailed off there, but in order for the machine to do a good job, it needs to know exactly how high the tool is. This is square, square. I have a ball nose somewhere. Square, square. There's a thread mill. What happened is I started breaking a lot of bits when I started milling things, which resulted in me going, oh man, I always need to have extra bits. So I got maybe too many, and now it's hard to find things. That is not it. Oh, here we go. Ball nose. The really cool thing about Tormach machines is that so all of the tools that they make, if you enter the number, there's a number right here for this part. So 37367 is the number of this end mill. And if you enter it into the machine knows what that end mill is. You don't have to like give it all of the extra information. So we're going to take a couple of sketchy measurements here. Okay, how am I going to measure this? It's close enough. I need, let's go with like 0.86. And so this is a tool measuring thing. You get your tool on the block. The block is totally flat. So we get it on there, we hit 0. Actually, what I want to do first is 0 here. And see how high I go. So that's not quite enough. I want a little bit more stick out than that. So we'll pull the tool out just a little bit more. 0.9, that's plenty. Then I use these wrenches. And tighten down that tool. Okay, so then take this, we put it down there, 0, we bring it up, and our tool height is 3.1305 inches. So I'm going to go put that in Fusion. This is going to take a hot minute, and I will be back. 3.1305. Yeah. Okay. Let's get this show on the road. 3.1305. Now we need to put that in this. 105. Let's do this. So you can sort of see what we're working with. So we go into our tools. I listed it as tool 17 for no reason. This is actually that, no, it doesn't matter. Okay, well, we can just do this. I'll show you how cool this is. So I have the tool number here, and I go 37367. And it autofills all of the stuff about this tool for me. Oh, it's 3 flutes. I thought it was 2. It doesn't matter. And the length, one more time, 3.1305. That is a really important number. 3.1305. Okay. So this is tool 17. We're going to tell our machine that we have tool 17 in there. This is our tool path here. And we're going to load up the new tool path. Tool path parallel, load G code. And so this is our new parallel path. So it's just going to go back and forth on the object and make a ton of really tiny lines. This is all individual passes here. And that's our plan. So tool path parallel, we have tool 3. Why is this saying tool 3? This doesn't look correct to me. I'm going to double check things in Fusion. 1 second. Okay, try that again. Here we go. In offsets, or sorry, file, parallel 2, load the new G code, and now we can see it says tool 17, and this is our path. So let's put the new tool in. Can switch my view. Take our new tool. And I'm just going to advance it really quick down to the bottom. We have tool 17, and what I want to do is check. Oh, we can't really reference the initial XYZ, can we? Yeah, that's too bad, because we took off that top layer. Yeah, that looks about right to me. And if I wanted to get to the very top, sorry, I'm like talking to myself a little bit. This is almost touching. And that's like pretty much touching. Okay, this is accurate enough for me. Is everybody ready? Should we run this thing? I've missed a lot of chat, so if you put things in the chat, I will get back to you soon. We probably don't need coolant for this. I'll leave it on, but like, I don't see a huge point to it. Let's get this camera over here so you can get a good view of what's going on. All right, ready? Parallel 2, we've got the right tool in the holder. We've done a little sanity check in the Path Pilot controller. Let's run it. And we're starting at 50% feed rate. That's a fun noise. I think we're taking off a little bit more than we intend to. That sound is not very nice. Woo! That's a little sporty. Yeah, so this is going to result in a nice finish, but it's a little sporty. And the chatter is not great. I was going to say I thought I got my tool length wrong, but it kind of feels like I got my tool diameter wrong. Or a little of both. We're cutting off more material than I thought we would. It does look really pretty. Did you have a negative stock to leave setting in your cam? I don't think so. I'm going to go double check that. It shouldn't change too much from here on out. It's just going across the part. I'll go check to see what happened. Maybe we had stock to leave in our adaptive paths. That might have been what it is. Yeah, it's we had about 2 thou of stock to leave in our adaptive paths, and I didn't catch those. So when we came in, we definitely are, you know, like removing material. We're removing a little bit more than 2 thou, I think. Yeah, I think we're removing a little bit more than 2 thou, but that might also be like problems in tool measurement. Like we're trusting this 1/8 inch tool measurement that was on the previous op. So the flat end mill may have a measurement that's slightly off since it's a little older. And then this measurement, which we know is pretty accurate just from doing it today, may be, I don't know. So maybe we left like a few thou of stock to leave. We intentionally left 2. Well, unintentionally, but we did, by the machine, we left 2. Both radial and axial stock to leave. So that is at least part of what we're cleaning up now. Anyway, good call on the ball pass. I'll tell you what though, the finish on this looks really nice. Do you have a Kalman gain per sensor, or is it for the complete system? So I can't remember what the Kalman gain is in this context. I have process estimate error. I have process error, which represents the error both in the model, like my attempt to model the system, and it combines that error with the accelerometer error and assumes that those are the same, because the accelerometer is the only thing feeding into my process step, or sorry, my prediction step. So there's prediction error, and there's like sensor noise error in that, and that accumulates until we run the update step, which is GPS, LiDAR, barometer, whatever you might have, and those have their own gains. But I think the answer to your question is like you definitely have different gains for different sensors in terms of the measurements that you update, but I do not update I do not have a separate process estimate and sensor for the process estimate gain, or like sensitivity. Wouldn't it be faster if the CNC head was moving back and forth, or what is it? Back and forth instead of sideways. You're covering the same area either way. But I want to do it this way because this is the direction that air is flowing, so it's a little nicer to have these smooth passes go this way. The Kalman gain is how much you trust your model versus your sensors. I understand. So to answer your question, I have a separate gain for sensors when we update them than I do for the model. But that separate gain for the model factors in the noise of the accelerometers. That is one number to represent my inability to model the model and my inability for the sensors to estimate the model. It's really hard to do this without like a whiteboard. All right, we're getting there. We're about a third of the way through. It looks really good. Like, this was definitely worth doing. I'm gonna get a longer HDMI cable so I can see if I can show you the side. All right, we're gonna switch angles for a second. There you go. Is milling lubricant still flowing? Yes, it is. How do you end up knowing what your Kalman gain is? Is there some way to calculate it based on sensor specs, or is it relative to a more accurate sensor? So it's sort of two things. If I understand what the Kalman gain is, at least in what, like, if I understand the term that we're talking about correctly, there are two things that factor into your Kalman gain. One is calculable, which is how much noise your sensor is putting into your estimate. So if you have an accelerometer and you're tracking how high the rocket goes, you double integrate it to get position, right? You integrate the accelerometer, you get velocity, and you integrate the velocity and you get position. And when you have that acceleration measurement, there's some noise in it. There's some error in terms of like how good that sensor is. So this is the first part, which is that like you are accelerating and you're trying to measure that acceleration and factor that into your system, and there's some amount of inaccuracy. So that's part of your common gain, and that is the part that is really easy to calculate. Like, you have measurement noise, specs, you have all sorts of things that are like mathematically easy to figure out for what your sensor noise correlates to in terms of your common gain. However, there are a couple of things that assumes. First is that the noise is Gaussian distribution, which is like it falls along that regular Gaussian curve, which is not really true. That's an assumption about how noise works. The second is that it assumes your sensor noise is constant. You could adjust this, but like as you get into higher ranges of your sensors, sometimes your accuracy goes down in ways that you like don't expect. So there's all of like that stuff, and then the second part that I think is easy to forget, I forget it all the time, your model, like the model that you're trying to estimate, is always flawed. So any estimate of your model that you have is just that, it's an estimate. When you describe how the accelerations translate into your position and velocities, like you're negating a lot of like you're looking at it from a really basic physics perspective, and I don't know how to describe exactly like what all of the other things are, but like a linear Kalman filter takes more assumptions than an extended Kalman filter, and so that part of determining your Kalman gain is a lot harder. You can't it's hard to quantify how off your model is from reality. So you have to make a model that is as accurate as possible and then use that with respect to your sensor values. Yeah, if you wanted to get the most mathematically ideal thing, a Kalman gain, then you get, or like the most deterministic Kalman gain, you make your model really good. And then you can back out like your Kalman gain from your accelerometer or whatever you are using to update your prediction step. The problem with that is it takes a lot of work, I think. Like if you really wanted to make a super detailed model, I don't know how you'd go about doing that. And beyond that, like you can also just test a bunch and then tune it. That's a lot of what Kalman filter tuning is tuning that one little gain. You have these pretty accurate noise estimates that come from your GPS or your barometer, but what's hard to determine is how good your model is. So it's already difficult to come up with a mathematical solution to that. So the better thing to do, IMO, is just test it a bunch. Will you be releasing a schematic for Ava or Signal? I probably will not. Ava is quite the computer, and I don't mean to be selfish, but I worked really hard on it, and it's not that hard to design one of these yourself. I have some tutorials on my channel about it, but I don't want to release the schematic for that. Also because then I'd have to release the code base if I really want it to be like a comprehensive thing, and I don't want to do that either. And then for Signal's a commercial product, and it's not built to be programmed by other people. So releasing the schematic for Signal means I also have to show you how to use the piggyback board, and really you should just use Signal with a USB port, and at that point you should just build Blit. All right. I'm happy that you took my advice and get the head moving back and forth. Yeah, that's definitely what I did. Getting there, folks. What is a good microcontroller to base your first flight computer off of? I like any of the stuff that Paul Stoffrigan from PJRC does. So he makes those TC microcontrollers. Those are really good options. A lot of Arduinos right now, anything with an M0 chip is usually pretty good. Out of context, but love your video style. Thank you. What camera and lens do you shoot on? Oh man, I love talking about cameras. And also, like, there's no out of context. There is no context on this channel. So this camera here is called a Z-Cam E2. It's a camera I bought back in 2019, like late 2019. And it's basically, it's like a baby cinema camera. So the camera body, I think I paid, it's either $1,000 or $2,000, but it's just the body of the camera. So that's like the brain. So you're not getting the lens, you're not getting the screen, you're not getting a handle, you're not getting a cage. There's all of this stuff that like has to get purchased with the camera, which is kind of annoying. But it's a really good camera, especially for tracking rockets. I quite like it. That's the thing that I shoot like talking segments, sit-down segments, and tracking shots with. And it used to be the thing that I filmed everything with, but it's really big and it's really hard to hold and like run and gun. So then, last year, right before we did the Christmas tree, I got this thing. So this is a Sony a7 III, and I bet it's cheaper than when I bought it because they have released like 2 or 3 new models. But it does 4K, it doesn't do like crazy high frame rates or anything like that. Like the Z-Cam does 4K at 120 frames per second, and this is just regular like real-time 4K. And this thing's awesome because it's so tiny and lightweight that you can just like hand it to someone and be like, point it in the right direction, and the Sony will figure out the rest. As for lenses, this has its own like, this is a different lens now, but it's like a 24 to 105 type thing, like a most good ranges type thing. And then the Z-Cam I use also a 24 to 105. Even for tracking rockets, you actually kind of want a wider lens unless you are really far away, because rockets jump off the pad so quick. If the rockets I flew had a much lower thrust to weight ratio, I would use the 70 to 200. Anyway, that's a lot about cameras. Almost done. We could probably speed up this op if we wanted, but it's fine the way it is. I'm in no rush. Alright, I'm going to skip a couple of these. If you were making Ava again from scratch, would you consider using the RP2040 for the nav main core instead of the Teensy and the other one? Probably. Cameron, is the Raspberry Pi thing multi-core? I would do Ava as multi-core if I were going to do it again. That's really what it should have been, but I don't think there were quite as many options out for it at the time, or I just wasn't looking hard enough. But transferring data in between the nav and TLM and main processor is a real pain in the ass, so I would do multi-core. Can we get a quick quiet on the set? Yes, absolutely. Quiet on the set! When are you getting a Phantom 4K? What is a Phantom 4K? Like the drone? Oh, the Phantom Flex. Oh, those high-speed cameras. Those things are crazy. Excuse me. I do not need one of those. Does the engine layout and gimbaling of the Starship model rocket work? Can you catch it? I don't have a lot of answers for the Starship model yet. I designed like some of the Starship and none of the Super Heavy, and then like haven't touched it in a few months. So I'm pretty focused on Meat Rocket right now, and we'll get more stuff about Starship probably this winter. How did you learn to integrate microcontrollers into PCBs? I ripped off a bunch of schematics online. Arduino and a lot of those style of boards will usually publish a schematic of the thing that they've made. So you can find one for an Arduino Uno, you can find one for an Arduino M0. Teensy, like PJRC publishes the schematic for his Teensy board, so you could take the Teensy board and make it into a more Ava or like Signal looking board. So I just took those schematics. I didn't do a whole lot of circuit design myself. I just knew that those worked, and I ported them onto my own boards. Why are there so many resistors and capacitors on some circuit boards? For signal processing, where can you learn these applications? Same thing as the previous answer. It's just signal like stability usually. I mean, that's like, how do I answer that? That's like asking, where does a car take you? And you're like, well, a car can take you anywhere. Like a resistor can do all sorts of things. It can help condition a signal. It can help divide voltage. A capacitor can help store like voltage if you have voltage spikes and help smooth out your power signal. It can also help condition signals. There's all sorts of things that both of those devices can do. It's a dual core M0. Yeah, that sounds pretty good. I would have to look at it, Cameron. But the RP2040 does sound good, at least for those specs that you showed. Have you ever considered showing up to one of those collegiate launches like IREC for fun? I show up to college launches all the time. I get a ton of like personal fulfillment seeing college teams trying something that's really hard. So like a lot of the liquids launches that happen out of FAR, especially if it's a college team, if I'm not working with the team, like I'll still sometimes go out. So I went out for Purdue, did a rocket called Boomy Zoomy. They actually did it like 3 times, but their first attempt I was out there with them just to like help and film. And then I was out there for the first attempt, or one of the attempts of the Altair launch from Embry-Riddle. It did not work super well, unfortunately, but I love going out to that stuff. I think it's really exciting because all of these college students like are not. There's a lot of people in the real aerospace industry who are super jaded, and a lot of these college students, just by being new to it, have like massive amounts of hope and drive, and it's really fun to see. Any more cooking or baking with Joey B? Sure, we could do some more. I don't have anything planned, but you gotta eat, so I can cook. Respectable shirt. Thank you. The forklift certified. You have no idea how large of a source of motivation you are for us college students. Oh, thank you so much. What team are you on? Hi, Ben. What was the last thing you 3D printed? The last thing I 3D printed was a part for this camera spinner thing that holds all of the gear shafts so that they don't wiggle around a bunch. What launch are you going to next? I am going to... So I wanted to go to FAR this month, but my sister got married on the 15th and I was out of town on the 1st. And those were both of the FAR dates for October. And then I was like, oh cool, I'll just go to the one at the beginning of November to fly then. And I'm co-emceeing with Zyla Foxlin this space gala that's happening in Florida, so I can't go to FAR then. So the next launch that I'll be at is out at the Lucerne Dry Lake Bed, and it's called Rockstock. So it's a rocketry organization of California. It should be a pretty big event, should be a bunch of people there, but I'm going to fly send it with this, hopefully spinning and stabilizing the camera footage. Do you have a GRA? I don't know what a GRA is. Team 85 for the University of Buffalo. We launched a 10K SRAD rocket quite successfully. Hell yeah! Nice! Did you recover too? It's the hardest part. We need more build streams. I'm down to do more build streams as long as it's okay that I do them on the Joe Barnard channel. I think sometimes doing long streams like that hurts the channel in terms of algorithmic stuff. I don't know. Maybe we can try it again. Space Gala with you and Zyla. Yes, you can get more info on that. Here, I'll get the link. started. So, here's the link. It's a gala to celebrate a bunch of women in STEM, and this website will be able to explain it much more than I can right now. I'm kind of focused on this stuff, but it's going to be a really fun event. Should be a blast. There's a bunch of other people going, but Zyla and I are co-emceeing, and then I have a bunch of friends who are going as well. So it should be pretty fun. What part is this, and what will it do? So this is a camera fairing or camera housing, and it's a little hard to see from this angle. Maybe I'll move the camera, but it protects the camera from all of the aerodynamic nonsense that's going to happen on the meat rocket and on Send It. Okay. Alright, almost done with this up. And then we're going to flip the part over and carve out the inside. Alright, this looks good. Does anyone have any objections if I take this out of the vise? I don't think there's another op that we need to do. And I can blow some of this off here. Woo! Oh, this part looks nice. This is really nice. I'm glad we did these passes. This was totally worth doing. Wow. That feels great. That's super smooth. Whew. Okay. Well, that's great. Time to take it out of the vise. Is this to house the new GoPro? So the new GoPro is too big. This is still going to be those run cams that I like. Yeah, unfortunately the new GoPro is still too big, at least for a 4-inch rocket. Okay, so let me show you what's happening here. Okay, so this is the part as it stands. Those parallel paths came out really nice. So we've got like a pretty smooth surface. You can't even, like, you can almost not feel the ridges here, which is great. So this looks really good. We're gonna take this, flip it upside down, and then we're gonna carve out a channel in here. And when we carve that out, what it's going to do is, wait a minute. No, this should still work. When we carve it out, it's going to leave a little relief so that inside here we can put the camera. So this part gets mounted inside the airframe. Like this. And a 4-inch rocket. This goes up inside the airframe and it sits, see that lip right there? So it sits up against there, and then the camera is inside this section and it points down the vehicle. So the profile, like, you know, it's not amazing, but it's going to let us get some really good footage. So we're going to carve out the inside section, and it's going to protect the camera really well, is the big key here. Okay, so we're going to hold on to it in a slightly sketchy way. Oh, I didn't tap it. Hold on. Also, you guys should get the GoPro angle here. Okay. Oh, took a chunk out of that. So the first thing that we're doing on this is the 1/4 inch. Which we did before. some new G-code. Load G-code. This is the see who it bought. Load. Cool. This all works. Okay, so we start off with tool 2, which is this, and we're going to check our Z top. And we're going to have to retake our other measurements. You know what? Let's get the sides first. Whoops, that is the wrong direction. All right, so we're going to take this. This should be almost identical to what it was before. But we're going to first find our Y plus. I'm going to go down a little bit. All right, find Y plus and set origin. Oh, tool 99. So what we're doing here, I'll try to give you a view of what's happening. We are using the probe to find all of the different dimensions for the part, or rather, we're trying to find the center. So I'm going to go up. I just probed this. If I do it again, why is that offset so much? Oh, I get it. I know why. So we're just touching the edge of the part, and then that feeds it back into the controller, which says, okay, cool, I know where that edge is. So now we're going to go down here, and we're going to find the Y minus. And the reason we do this is because our work coordinate system, or like the center of the work coordinate system, is right in the center of the part. I did that intentionally. I can explain it a little bit later if someone re-asks, because I'll totally forget. But all right, find Y minus 9961. Do it again. Okay. Actually, wait. Y minus. Yeah, that's fine. So then the way that we'll set the center is I go to what's 9961 over 2. Oh, 0.49805. Oh, 0.49805. Cool, that's close enough. So we're going to 0 the Y. Now we're going to do the same thing on the x-axis. So we're going to find x plus. Okay. And probe it again, just for good measure. Cool. And then find x minus. Okay, 2.9905. What is half of that? 2.9905 over 2. 1.4952. 1.49. Cool, there we go, 0. And now, we can get the actual tool in there. Which is the 1/4 inch bit. And we can find our offset, putting a little piece of paper under here, and then going down until it starts to scratch. All right, and this, what tool is this? This is tool 2, right? 1/4 inch, tool 2, and that is Z0. Okay, how are we all feeling? Are we ready to rumble? This feels good enough to me. I think we send it, right? Are we all in agreement? Should we just send it? Oh, let's make sure the coolant looks good. All right. We've got a good comment, good super chat here from Ben Reedford, $2, and he says, bacon, egg, and cheeseburger soup. For sure, dude. Like 100%. I'm in total agreement with you on that. All right. Send it. Here we go. Let's record on here, just in case something funky happens. We've got our see who had bought one. We're just gonna reload. Yeah, bought one. G code. And this looks like the right G code. Okay, I'm a little nervous. I'm also wondering if these parallels are gonna be enough. Because we go pretty far down. Minus 0.79. You know what? We can check this. We can check this. We're better than this. I can find out if we're going to crash before we do it. Okay. We are going to crash if I do this. So, the problem is I don't have parallels that are higher than this. So what do I do about that? How about we do sketchy work holding? The part will center itself, he says confidently. Now this is a really bad idea. You know what I need? I need like shim stock is what I need. Also, I wonder if I could do 2 sets of parallels. Let's just see something. No, these are the same division. That's not going to make a difference. I could just send it, but that's not a very wise choice here. Because I really like my milling vise. But I just need this to be like a little bit higher off there. Oh, here we go. Okay, everyone close your ears. Okay, no, my blade does not like doing that. That's fine. I think it would be better if I just cut it. My tin snips are in the other room, though. All right. One moment. I think this is going to work. I kind of think we should send it and then try to dial indicator it in. I think that's what we're going to do. Yeah, that's my new plan. Okay. So I have this, and then we're going to get the dial indicator, and we will manually see if we're parallel. And it'll be good enough. Okay. So now on the X, see, there's a bunch of run out there, right? So what we do is we do a little percussive persuasion. Gotta be really careful about the indicator here. Also not doing this with the right hand. It's really hard to do this with a camera in your way. Whoops. That's probably too much. Oh, that's not so bad. Hey, look at that. I could call that good enough. All right, great. That's good enough for me. All right. So now let's see what the situation is. It's 7-9. So what we can do is get our new 0 first. This is a lot of work. It's weird making like short runs of parts. Is this tilted? No, not really. It's weird making short runs of parts because you do really sketchy shit like this. That's fine, normally. Okay, so we're gonna go this far down. Awesome. We're gonna clear it. Yeah, all right, great. That extra like 0.05 inches totally makes the difference. Yeah, like I'm doing a bunch of one-off stuff. That means we do all of these kind of sketchy ops. Because it's not worth the time to make a bunch of tooling to hold your parts for like 2 parts. Okay. Ready? Should we run it? We've got our zeros. If I bring this down to 0, this is definitely our origin. Okay. Let's try this again. Okay, rolling, send it. So we're going to take it a lot slower for this one because we're not holding on to the material very well. Right? Like we've got this huge diving board and we're holding on to like 2 millimeters of material. Alright, I've missed a whole lot of chat. Thanks to everyone who's hanging out. Someone says, hey dude, how are you? I'm doing well. Unless you were talking to someone else, which, who knows. Yeah, tolerance is good enough. Someone asks for the cutting milk. The cutting milk is active. We're just not using a lot of it. I also wonder if that diving board will find a resonance. You and me both. We are both wondering this. You can tell, especially in these moves, that my feed rate is pretty slow. I'm running at 36% of like what the actual feed rate should be. And because of that, we're making some pretty small chips, I think. And it looks like we're going to clear this whole top layer off. I thought I saw aluminum in here. Alright, my camera is running out of battery, but I want to watch this op finish. Okay, we're doing well. This is like working. Alright, my camera is about to die, so I'm going to switch to the GoPro, and then I'm going to replace this battery. One sec. There we go. Back in action. Oh, shout out Canine Rocket Technologies, electricity build for RGB. Thank you so much. Here, let's get some RGB up in this. Woo! Thank you for the super chat. How well can you see on the GoPro? The GoPro kind of comes across, but the GoPro's all over the place, TBH. Do I have effects on this? What's going on? Ah, you can see it better there. We can probably increase the feed rate a little bit. Joys of adaptive milling. Alright, we also don't need this much coolant, I don't think. Alright, if that diving board is going to find a resonance, this might be when it happens. Duncan asks, just wondering, was Altair the highest accelerating rocket with Ava on board? So Duncan, do you know what was your acceleration at the liftoff that y'all had? I think the answer is no, but I'd be willing to give it to you out of respect for losing that rocket. Also, BRB. Woo! Making some thin cuts there. Woo! Duncan, 95.9 Gs. Okay, it might be. So I had, if you know Neutronium 95, he's in the BPS Discord. He's around. This dude flies crazy high G rockets. I can't remember what the highest acceleration he had was, but I don't think anything has clipped like 70 G, maybe 80 G with Ava. So I actually think you legitimately have the highest accelerating rocket. I think you've won that. That also means, I don't know if you guys have tried to power on the Ava since that flight. You should have basically infinite flight data, just from how I know, how Ava works. So I don't think you're going to be able to get the data off yourself, because that's sort of a... Anyway, once I get the Ava, I should be able to extract that, and we'll see how hard you accelerated. But my accelerometer is capped out at... They cap out at about 64 G, so I think you... I think you get the record. Oh, shout out Dub MFG. Glad the Tormach is working out for you. Thank you again, dude. Thank you very much. I hope all is well. Even a small desktop CNC is a little bit terrifying on your first run. Wonder how it felt doing the first job on the Tormach. Tormach actually made it pretty easy because it's a there's a bunch of like operations that you can do within the machine. Like it'll let you do all of this little, they call it conversational milling, but it's sort of like if you had a manual benchtop, or not benchtop, like a knee mill, or like a bridge port, that kind of thing, where you're rolling the little pulley thing, whatever you call it. There's a bunch of stuff that you can do on the Tormach that's not a full like CNC program, which helps get comfortable. This is aluminum 6061, yes. I do use coolant. I don't use flood coolant because flood coolant doesn't work well if you let it sit for a long time. It gets disgusting and gross. And I also need to film videos, and videos look a lot better if you can see what you're cutting. So I'm happy to go a little bit slower or take like less aggressive cuts without using flood coolant. How does a rocket flight computer detect a launch? Working on my own Arduino. So I detect launches in two ways, and Duncan's scenario is actually pretty unique. If anyone saw, listen, I'm not going to like advertise what happened to their rocket, but it wasn't good. It accelerated very hard for about a foot, and then it came back down and stayed on the launch rail. A little bit hotter than it was before. Ava detects launch in one of two ways. Oh, we're cutting air. Alright, well that's fine. Ava detects launch in one of two ways. Either you have to be accelerating like at like 2 Gs for, I don't know, it's like a half a second or something like that. So that catches the really low TWR stuff. So like, it sort of varies rocket per rocket, and there's a setting in Ava which lets me set the detect criteria. But on like a really high G launch, you know that you're probably not going to have the rocket feel, you know, let's say 20 Gs in a normal scenario. Especially if you're powering on the pad, you could safely set just one gate that says if you feel 20 Gs, you've launched. And you want to detect as fast as possible so you can get your filter updating and like change states on your flight computer. The other way that you can do it, there's a couple of ways. You can do it via the barometric pressure. If you see that your pressure is dropping really, really fast, you know you've launched. I never have a full, like, you shouldn't have the ability to read your sensor once and that one reading trips you into the launch state. Assume that you could have crazy spikes and noise. So instead what I do is I say, have you been accelerating more than 20 Gs or 15 Gs or 10 Gs for 50 milliseconds? And we read these sensors really, really fast. So if you have constant acceleration like that, that's going to rule out the hit of a hammer. That's going to rule out like rattling around on the launch pad. And that's been pretty reliable so far. Altair's acceleration was so high that the nose cone got shoved into the airframe a 1/4 inch. Listen, I'm sorry. What happened to your rocket is very sad. That's insane. That's awesome. Hand wheels, that's what they're called. Thank you. We have some small CNCs at work that use conversational code. Just give the machinist a drawing. Yeah. Yeah, the rocket it seemingly did become the flaming end. Alright, still going well. We're cutting a lot of air. I'm going to be honest, I'm a little worried for what happens when we get down to the very bottom. like it should be fine. But we're taking away a lot of material, and that vise might start to bend apart. Sorry for not talking. I'm trying to grab some sick clips. This is going to be a little bit hard for the encoder. Woo! Party mode! A vertical spacer has fallen over. That is correct. It's not really being used anymore, so we can actually remove it. OSHA would not approve. OSHA would not approve of what I did. That is correct. Woo! Crazy! Party mode! Pretty crazy. All right, I think maybe we've had enough party mode for a bit. That's a little nicer. I wonder if I... All right, what else we got going on here? Sketchy fingers, OSHA doesn't have to know. Oh, it's a Barbie bathtub. Indeed it is. Talking about encoders, have you thought about using servo motors with encoders on TVC stuff instead of a time delay? Servo motors with encoders instead of a time delay. Do you mean like the refresh rate? Can you give me some more details? I don't know that I totally understand the question. While you were machining, I glued an iMac display back on, and I finished without breaking it or forgetting to plug in the display. Can I get some praise, please? Yes! That's really impressive. That stuff is really hard to do. Apple does not make it easy to service your computers. That is really impressive. Also, Hannah says this is looking so awesome. Yes, it is! and like surprisingly smooth in terms of how the process is going, which is great. We have to make one more of these, and I've been streaming for almost 3 hours, but making the second part should not take as long as making the first. Making the first part takes the longest because you're going slow with your tool paths, you don't know how things are going to work. So after this, I'm going to regenerate tool paths to include that parallel part, so it's one big tool path on the first top side, and we're going to make a second one of these so that we can just be done with it today. This is the first one I made. I have not made the second one yet. We're not going to do the parallel path. We're not going to do the parallels on the inside of the part just because it doesn't need it. It would look nice, but it would cost a little bit of time. And there's also a risk, like with how good or lack of good I am at machining right now, there's always sort of a risk that I break a tool. And so I'd rather not... I don't know that I have a second ball nose end mill, is sort of what I'm saying. Let's try to get some interesting shots here. I have an idea. Just trust me. This is a pretty cool view, right? So what you're seeing on your screen is basically in the center. Those are all. That's the G code. Those are all the G code instructions, and then you can see what the controller is commanding the tool to do on the right-hand side of the screen. And so this is the Path Pilot controller. And if I tilt down a little bit, you can also see the actual position of the machine updating. Okay, so I'm going to turn off my webcam for a second. So basically, oh boy. Okay, so basically, you have your position in G54, which is like a coordinate thing, and that's the actual position. In those white boxes on the bottom, that is the actual position of the machine, and then there's these other numbers called DTG, which is distance to go. So there's like where the machine is and where it wants to be. The DTG shows where the machine is trying to go in a given move. Anyway, it's really cool to see this like live feedback. Charlie says I might want to start with this op first for the second piece. It will be more rigid. I don't know that I agree with that, because the first op has, let's just take a look at this. I can't take it out of here yet. Hold on. Yeah, I think it's ultimately a little less rigid if we do it that way. Depends on how you skin the cat, though. Also, is this gonna crash? No. Okay. Let's run this. We need T3, which is the 1/8 inch. Okay. Yeah, live G-code. So PicoPlanet, is that built into the machine or USB SD card controlled? So it's kind of like, there's a computer in the bottom of the machine down there. There's a little Linux computer, I think it's Linux, but there's a little Linux computer that runs a software called PathPilot, and then if you see on this, it's like a computer screen. And so there's a computer that controls the machine, and the machine and the computer are separate. There's a whole electronics cabinet back there that runs like the stepper motors, and it drives like, I think some of the e-stop stuff, I'm not totally sure. And the controller just feeds instructions to that, and that executes the instructions. But you do still have to generate the G-code like in Fusion for your part. You can't bring a step file and put it on this computer, as far as I know. Is it hot? It's hot in the garage. I am hot. I don't know, maybe 10, 15 minutes away from starting to sweat. But that's just because I live in Southern California. Okay, watching your tuning videos, you commanded a position in your servo, and then using high-speed film, you calculated how long it would take the servo to reach that position. Oh! Yeah! I understand now. Yeah, the encoder is totally the right way to do that. Either an encoder or an IMU. And so the way that I've done it now, if you watch the Scout F engineering cut, I think I talk about it in Scout E too. Both of those videos, I talk a little bit about modeling the TVC dynamics. Is that a burr there? What's going on? That is a very tempting burr. Yeah, I talk a little bit about it, but I take IMU data and I use that, but it serves the same purpose as an encoder. So yeah, no, you're right. When I modeled it using the time delay, I really didn't I didn't think it through that well. I would not do it that way again. How does it receive G-code from your computer? SD card or Wi-Fi? So you can do either way, I think. I believe, hold on. So, I'm just looking at it now. The computer, actually, why don't I just show you? It's not that compelling of footage, but it's down here. So in the bottom of the machine cabinet, there's this controller called PathPilot. Right? And so PathPilot talks to this little gray translator box that's on the top. And the little gray translator box transmits it into this big B-sub connector that connects to the machine. But PathPilot is doing the work of deciding how to run the machine. And you can see these little USB things, right? So I've got two little USB things, and basically the machine has Wi-Fi now. So what I do is I go to my main computer, which is over in the other room, and in Fusion 360, when I tell it where to post, this machine is on my home network. So I post it directly to the machine when I generate the G-code. So I don't have to manage G-code files anywhere else. The other thing that allows is that I can store all of the G-code on the computer, on the PathPilot controller. So So if I wanted to make, hold on. If I wanted to make those parts from Send It or from Scout again, all of that G-code still exists on the computer, which is pretty cool. What is that big tank behind you at the wall? So, oh, that is my water heater. This is where my hot water comes from. Alright, I'm gonna go refill my water bottle. I'll be right back. Keep an eye on everything. Okay. I have watered 3 things. Let's see how this is. That still looks fine. I've watered 3 things. I watered myself with this. I watered my plants on the little windowsill. I got a couple of little plants to water. And I watered 2 very cute cats that are staying with me for a little bit. They are sleeping. I would bring them in here to show you, but they are very comfy right now, and I don't want to disturb them. Not one hit of no one hit the emergency e-stop unless an actual emergency. Wonder if you could develop a software that watches the YouTube chat or a Discord server or something to remotely e-stop. Brian, you totally could. I do love that idea. I just know how often it would be abused. Did some poking around in PathPilot. Looks like that it is both the controller front end UI and the controller box's name. It runs on top of Linux CNC, which is a Linux modified for real-time operation. Awesome! You know what? That means you could use Linux CNC as flight software. You want real-time OS for your flight software. What happened to Luna? Luna got separated into a couple of different plants. It's still alive in a sense. You want some cat pics? I can show you cat pics. Okay. There's a really pretty one from yesterday. Okay, so this is Loki. Very cute boy. Very orange. And then the other one is Mara. And this is Mara hiding under a blanket. She hides a lot during the day. She's not super social during the day, but she's very cute. She's also pretty long. Let's see. There's a couple good ones here. Here's another very pretty one of Loki looking outside. Very interested. Anyway, they're snoozing right now, so I don't want to bother them too much. I think we should speed this up. This is not that fast. And like, we're not taking deep cuts. So I'm going to go to 100%. Oh, that would be the right way to do it. Yeah, so you would maybe you'd use Nightbot to, yeah, Brian says you could use Nightbot to only recognize commands from whitelisted people. So like, you could assign the mods in the chat the ability to e-stop the machine, but a bunch of people who come in from outside, like, just to stop machines couldn't do it. I know you're done with Scout, but could you not put cardboard and Mylar on the bottom of the feet and have mini landing pads on each leg? Yeah, you could. You could do that. I mean, the problem with Scout is that, like, how do I say this? So Scout is really cool, and I love it a lot. The value add of continuing to fly it did not outweigh the value add of starting a new project. So when if you think of it from like the channel perspective, it is more valuable to like move on towards space shot stuff. You really I don't want to stagnate. I don't want to be doing the same thing that I have been doing for like 7 years. And so continuing to make sure the stuff that I'm building is like exciting and I get to push forward and I'm not stuck in the same design that I was stuck in 2 years ago or whatever. I landed it once and, you know, we learned that it wasn't super reliable. And if I were going to like make changes to the legs, I would make a lot more than just adding cardboard or Mylar to the bottom of them. I hope that's a good answer. Werner von Kerman says, did you the cat? And I don't totally understand the question. Instead of de-spinning the camera, couldn't you use a line scan camera that sweeps the entire horizon once per roll? I guess? But then it just means your frame rate is really low. I think that would be hard to do. Have you considered water-propelled model rockets ever? Water-propelled stuff is fun. I don't care that much about it, but I know that people like it a lot. How is the mini lathe working out? What model is it? Here, I'll show you. So, this is the Tormach. If I back up a little bit, I can show you. So this is the Tormach, and And then I've got a workbench with like a drill press, and there's a chop saw, and then this is the mini lathe here. So it's whatever this is, CD210B. It's also a little damaged. You can see some like damage around. It showed up in kind of tough shape. There's also a lot of brass shavings down there. But it's good. I bought it, hold on. So the reason I got that particular lathe is because the dimensions were the biggest. I wasn't looking for anything that could do like crazy high precision. I was looking for something that had a really big swing and a really big like tool post to tool post, or what is it called? I guess tool post? Either way, not tool post. What's the end stock called? Tail stock. Between the stocks, I wanted a really long length, so it's 8-inch swing and 16-inch between the stocks. Now, that gets cut into really severely by the 3-jaw chuck. It gets cut into by whatever you used in the like M2 taper or MT2 taper of the tailstock, like whatever goes in there to center your piece, that gets cut into too. But I've got this piece of aluminum here. So this is going to be the fin can for the meat rocket. It's a pretty hefty piece of aluminum. It is a 1-inch wall, and it's 12 inches long. It's going to get cut down to 11. It actually might get cut down a little bit more, but 11 inches end to end. And then almost all of the material gets removed, except for the material that we need to hold 4 fins on. So this is like an actual can. Like when you talk about a fin can, this is a can. And it was not cheap, so I hope I don't mess it up. Meat rocket. Hoppy says, I accidentally gave you a lot of views on TikTok because I posted a vid that got over 7 million views and you were tagged in it and the dates line up for when it went viral. What's your account name? I honestly, I don't really know how TikTok works. And did you tag my personal account or the business account? The BPS one? That is a lot of material to remove. Oh, I should have clarified. The lathe is sort of up to the job. The only thing I'm doing on the lathe is turning the inside of the part just a little bit. And I might not even do that. We'll see. SpaceX update or Universal Rockets. Okay. Yeah, the lathe is only going to turn the inside of the part just a little bit to smooth out that inner surface so that we can put it on a fiberglass tube. And then what I will do for the rest of the part is I got the 4th axis. So, alright, a lot of heavy things right now. This is the 4th axis for the Tormach. So basically, it's a harmonic drive rotary axis that you put on the Tormach, and it allows you to spin the part in the machine as part of the CNC program. And this will let us, ideally, over the course of 12 hours probably, mill out this part, the big fin can. Whew. All right. What else is going on here? Are you removing material from the OD, or are you planning running a foot-long boring bar? It's a foot-long boring bar, Brian. It's gonna be awesome. Oh boy. Woo. That's about as close as the tool could get without breaking anything. And I think that is the end of our op. So it's fairly smooth. Got a bunch of burrs in here. You know, we could come over this with like the parallel tool with the ball nose, but I don't think it's worth it for the inside, just in terms of the time. Also, this is a pretty solid part. This is like thicker than I thought it would be. And then the only thing I want to check before we take it out of here is, does the run cam fit? So let me go grab one. Okay, there are 2 run cams that need to fit in this device, this part. Oof. Okay, the first one is the run cam split 4, which fits great. That's plenty of room in there, so that's going to be looking down the side of the rocket. And the other one is the run cam hybrid 4K, I think it's called. And this just fits. I'm talking about the side to side, so like this distance here just barely fits, and that's perfect. This is sort of what it was designed to do. So this is really good news. Feel good about it. I think we could pretty safely hog out like another millimeter of material here, but I'm not going to do it. I don't think it's worth it right now. Keeps the part really, really strong. And yeah, this is fine. When we're looking down the vehicle, it's actually going to be looking a little out like that too. And I think I'd like to have like the lens totally submerged in there. This feels great to me though. I'm stoked about it. So I have to make another one of these, is the only thing. I think I'm going to take this out of the vise too. Any other parts I should make before I, or any other ops I should do before I take it out of the vise? I don't think I need to. It looks pretty great as it is. Yeah, it's a Sumark-esque fin can. It's actually, I took a lot of inspiration for what he did on his fin can for the 38 millimeter, and I've seen some people do it for larger rockets too, so I figured let's just try it. Clean it, more CNC party. Let's just take it out. Here we go. I totally forgot that we clamped it in that way, that it was totally just like freestanding. Here, let me brush this off. And you can take a little look here. So this is the part. And it looks great. Look at how smooth that finishes on top. Really nice with that scalloping, or whatever you want to call it, the parallel pass. So this goes inside the vehicle, right? So we've got our airframe, and this goes up inside like that. And then you make a cutout, and the camera can live inside there. So that's sort of the goal. But yeah, this looks good. And then, as I said before, like the inside isn't really cleaned up. It just looks like we were trying to remove material, which is true. These are also like, these are much thicker than they need to be, these walls. But it's not a big deal. It's not a very heavy part. It's aluminum. Yeah, and I feel great about it. Let's see, what else? How's everyone doing in the chat here? I can't believe it worked that well in the first try. I guess I'm getting better at CNC. I don't think I'm very good at it, but I'm getting better because a lot of my ops that I've done before have not gone that smooth, especially on the first try. Where did you get your small run cams from, and how much do these small ones weigh? The small ones, which are very tiny, by the way, and here's one. So these little guys are probably about 10 grams. I think I've seen it somewhere. They're 10, 15 grams. I got them from Amazon. You can buy them from a bunch of places. They're basically like remote control, like racing quad type cameras. So they're supposed to be extremely lightweight. It's as much as they can pack in this little lightweight package. And it's really tiny too. So I love them for rockets if you can provide the power they need. Okay, what else? Hey, just an idea, but I thought in the future it would be cool if you make the Sea Dragon rocket and launch it in wire. Those slow-mo shots would look insanely cool. They would. A water launch would be pretty sweet. I would need a good pond, probably someone with some RC boat experience. That would be cool. Am I going to do any sanding or polishing, just a machine finish? Honestly, for this, I could polish it. It would be nice to polish it, but this is like... This feels great. The finish is really good on this. I'm so glad we did that pass with the ball nose, with the ball end mill. That was the right call. What's the specs on those cameras? Oh, no side flanges to hold it into the tube better, or is it being held by the end stable enough? Oh, I think I know what you mean. No side flanges because it depends on like how you're going to integrate it into the rocket. But this is going to get covered in epoxy on the inside, and the forces here are going to push down and try to push it into the airframe, and the epoxy is probably going to do a pretty good job. We might actually do a screw, like a fastener on top of it too. What's the specs on those cameras? You should look it up because it actually varies a decent amount. Like the split 4s are really good. They'll do 4K and they'll do 2.7K at 60 frames per second, which is a pretty nice compromise. But the hybrid 4Ks, which are probably about twice as heavy, they also do 4K, but they can do 1080p at 120 frames per second, which is valuable for analysis. Like that really high frame rate stuff is great. Notice the radius doesn't go all the way to the edge. Is there an engineering reason for that, or was it just easier to manufacture? It doesn't go to the edge because the ball nose end mill, the ball end mill is, what do you call it? It took a deeper cut than we thought it would, and it's not really worth going back in there. I could take a file and do that if I really need to. What frame rate do they run at, and do they record slow-mo? You should look it up. There's a bunch of materials online that'll tell you all of the details for the different ones. What are you going to do for cooling? You were talking about not using flood coolant, but is it just compressed air and water mixture? It's compressed air and coolant. So there's a little coolant tank on the back of the machine that holds a bunch of stuff. And then I have something called a fog buster, which takes the compressed air and then it like puts just a little bit of coolant in there. So it's called mist cooling. 360 would be cool, but I noticed quality looks weird on 360. Yeah, the 360 is cool, but there are logistical problems to getting one of those cameras to capture the view that I want, which is looking down the body of the airframe. And I just hate the stitching that happens. I hate the look of the camera stitching between the lenses. So I'd rather not do a 360 camera on it. Are your hands over okay after you ran your hands in a bunch of metal chips? Oh, it's fine. The aluminum chips are not that sharp. Stainless steel chips or any type of steel chips would really mess up your hand, but it's fine with aluminum. Yeah, okay, I think I'm probably going to call it here for the stream. I'm just going to run these same ops again for a second part, but I'll focus a little bit more on grabbing nice shots on these cameras for video production stuff. I'm going to tell you what, though. Get ready. If you want machining content and you're bummed that I'm signing off for now, just hold your horses for like one little tiny minute because I got a ton of machining content coming up. That fin can is going to be a beast. but I've also got more aluminum parts to make for the camera mount. We have the nose tip section for the meat rocket that has to get made. That's some stuff on the lathe, some stuff on the mill. Yeah, that's pretty much it. Thank you all for joining, by the way. Sorry, brain fart. Thank you all for joining. It's been lovely. And I'll see y'all soon. Have a good one. Bye.